now let's talk about how to actually do structural steel design. This is in general the approach. We'll obviously get into specifics for different circumstances. So, yeah. So, what are the responsibilities of somebody who's designing something? This is for structural, but could be applied to other engineering designs as well, right? What should be your number one factor, or I hope your number one factor in designing is safety, right? Safety of the public and anybody using an engineered structure or facility. That is our number one priority. Number two, can it be built? And can it be built easily? And number three, cost. Is it going to cost a lot of money to build it? So safety, constructability, and cost. Ideally, cost would be at the end, right? Constructability and cost kind of go hand in hand. Safety number one, no matter what. So, how to be a smart designer, how to please your boss and the people that are building things, right? If we're talking about cost, choose sections that are readily available and nearby. Don't over design. This is a big temptation, right? Maybe one section needs a W10 by 52 and one, I'm making up numbers, and one needs a W10 by 48. Well, choose the 52 for both of them. You don't need to change your sizes by beams, right? So, and I just made up those sizes. They might not be real. And think about constructability. Will it be easy to make? Do you need a specialist to build it a certain way? That is one way to be economical. Another thing to think about, especially in terms of economy, is how do I get my materials from my fabricator to the construction site. That's why we sometimes have to break up tall columns, long beams, right? Is there an easy way? Maybe the nearby steel mill doesn't make the size you want and the closest one is like 1,000 miles away. Well, maybe you should rethink about which section you're going to use, because you're going to add all that transportation cost getting the air quote right one when it would be just the same as getting the one from the steel mill down the street. So those are all like cost things. Study typical failure points. I apologize, my daughter just went to the bathroom and the door was not shut. That was not me flushing the toilet. Look at your connections, check for redundancy, so that if one connection goes, does the entire building fall down? Hopefully not. If there's any type of differential settlements or settlements in your foundations, that's why the Leaning Tower of Pisa is leaning from differential settlements on either side. So these are all just things to think about when you're designing. So now let's talk about our design methods. We have, in our steel manual, we have 2 design methods that are used. LRFD, which is load and resistance factor design. And ASD, which is allowable stress design. The original design method was allowable stress design. It is what you will find in very old steel manuals. Let me think. They did, they had, how many? I believe they had 9 allowable stress design, right, that makes sense. They had 9 allowable stress design steel manuals. Then in the 90s, I think, they switched to LRFD. So there were 3 manuals in LRFD. 9 plus 3 is 12. For the 13th manual, they put them both in. So we have 1 through 9 ASD, 1 through 3 LRFD, and then number 13, 14, and we're currently on number 15, have both LRFD and ASD in them. Many things switch to LRFD, some things still use ASD. If you're working on something older, likely ASD. We will stick to LRFD But when you see ASD in the manual, and you're gonna have to ignore it, but that's what it is. That's what it stands for. Limit states. A limit state is something that you define for individual components. Like a beam, column, bolt, and it is defined as a condition in which, or a condition at which your component ceases to perform its required function, right? Probably should say like required. It is no longer doing what you put it there to do. The one that we always think of is strength. So, can it carry the load? Does it have enough strength to carry the load? Without excessive yielding, buckling, fatigue, rigid body deformation, that's where the beam just like spins. It acts as a rigid body and doesn't deform, right? So can it carry the load? That's defining its strength without excessively yielding, right? Once we reach the yield point, now it's gonna have a bunch of deformation, right? If we think back to our stress strain curve, we can apply, once it reaches yielding, we don't even have to increase the load, but it'll deform excessively without increasing the load. Or maybe you can increase the load a little bit, but it still has a lot of deformation. And maybe it's still working, it's still carrying the load, but especially perceived by the public, it wouldn't be good. Or you're gonna have too much deformation and your wall will be too far away from the column that's holding it up, or the beam, you know. So we don't want excessive deformations. We don't want something to buckle. Maybe it's, you haven't fallen down officially, but you've buckled. So that's the strength. Serviceability actually is kind of what we're talking about when we talk about excessive yielding as well. This is kind of, is it usable? You might have enough strength but be unusable. So this is where we talk about excessive deflections. Maybe you're starting to have some cracking, too much vibrations, too many vibrations, or some deterioration. What we focus on for the most part is the strength. Although serviceability can sometimes actually, it's a quick little calculation often, but it may actually control your design. You'll have to go with a larger section to have less deflection, even though a smaller section strength-wise would work. That's why you have to check both. So now we are going to talk about the two different design methods. If you go to chapter B, section 3 in the spec, which we will go over the what it means by the spec, but I'm about 2/3 through the book, through the steel manual. Section B3 starts on page 16.1-11, and we start to talk about LRFD and ASD. So using the LRFD method, we calculate an RU, which U means your required strength. R is just standing in right now for a tensile strength, a moment strength, compressive, axial load. So we have some type of required strength, RU, that you calculated from your loads using LRFD load combinations. That's where you go to AICE 7 and you say I have this type of dead load, this type of live load, I may have snow load, I might have wind load, earthquake load, and you use all the different combinations and you come up with your ultimate required strength. Then we have a phi factor. Phi is how that's pronounced, not phi. It may be pronounced in the Greek alphabet as phi, but it is phi in LRFD. And this is your resistance factor. And you apply that to Rn, which is your nominal strength. Right? That's where we use our material properties and our geometric properties of our steel section to calculate a strength. We apply a resistance factor to it, which is less than or equal to 1. So we reduce it. We reduce our nominal strength and we come up with our design strength. So RU, we calculate how much we need. PRN, that's how much we can get out of the steel section and property that we've designed. And you better hope that you have more strength than you need, right? We need our design strength to be greater than our required strength. That is the LRFD method. ASD is similar. We have our required strength, RA. Right? You again say how much dead load, how much live load, and you put them together in different combinations, but they're ASD load combinations, not LRFD. I'll show you how those differ. Then we have an omega, which is our safety factor. Again, our RN is our nominal strength. That doesn't change. But what changes is instead of multiplying by a resistance factor that is less than 1, we're dividing by a safety factor, which is greater than or equal to 1. Right? We're reducing it by dividing by a safety factor. And this becomes our allowable strength. We divide our nominal strength by a safety factor, and that's how much strength we're allowed to account for. And again, you want your allowable strength to be greater than your required strength. Different types of loadings. We've talked about it, right? We talked about this in structural analysis. We have our dead, which is everything that doesn't move. Because it's dead. I don't know. Live, that means it moves, so it's like people, furniture. What else do we have? Earthquake, snow, wind. That's all of them, right? Rain, maybe. Roof live load. Yeah, that's everything. We have all these different loadings, and we go to our load combinations. This is ASCE 7, section 2.4. We calculate all our loads, right? D for dead, L for live, live roof, snow, rain, wind, earthquake. Oopsies. Sorry, let's say chapter 2. Section 2.3 is LRFD. Section 2.4 is ASD. Now what do you notice? There's numbers in front of our loads for LRFD, whereas ASD generally doesn't, especially at, dead plus live. Anyways. So for LRFD, we have this load factor lambda. And then for both of them, right, you have this QI we have, for each combination, we have N service loads. Service meaning just the pure number, we haven't factored it. There's factored loads and there's service loads. Service loads don't have factors on them. Gonna write that. Right, just the pure dead, the pure live, pure snow, no factor. So LRFD, load and resistance factor design, means we have factors on the loads and factors on our resistance factors on our strength. Whereas ASD only has that safety factor omega on the strength. So if I'm comparing them, right, LRFD, I have my factored loads. Really not a lot of factors on my loads. For ASD, I use a resistance factor. Phi versus a safety factor, omega. In general, you can often calculate your safety factor. They're related by 1.5 over your phi. But you can see if I have factors on my loads and factors on my resistance in LRFD, so it's a little more engineered, it's less. The ASD is generally considered more conservative. Sometimes more conservative is better, but sometimes more conservative means it costs more because you're picking bigger sections, and bigger sections weigh more and cost more per foot. So typically these days, they've tried to switch to LRFD. That is what we will be focusing on in this class. We will be ignoring ASD. But I wanted you to see what it is because you might come into it, come across it in work, especially if you're designing something older, or if your company is using a different design approach, maybe an older manual. ASD might come up, but we'll be focusing on LRFD and LRFD numbers in this class. So that is a discussion on design approaches that will be used for structural steel design. Thanks.